Alrighty, grade 11s, we are looking at power and energy today. So we're going to look at them separately, but they are pretty much interlinked. If you've got one, you can quite easily find the other one. Okay, so first off, power. Power is the rate at which electrical energy is converted in a circuit. So usually we use the word dissipated. You'll say, the question might say, determine the power dissipated by the light bulb in the circuit, or you could do it for the whole circuit. Okay. Now, okay, so obviously you need to please know the definition off by heart, and then also just other important things. The symbol for power is a P, okay, and the units that we measure it in is watts. It's measured in watts, which is W as the symbol. Okay, now the formula for power doesn't actually come from the definition of power. The definition of power actually helps us to come up with the formula for energy, which is a little bit later on. But the formula for power is that the power dissipated by a circuit or by a specific component in that circuit is equal to the product of the current and the potential difference through that circuit. Oh, it's the other way around on your sheet. Sorry, I don't want to confuse you. Okay, so still multiplication, but now it's V times I. Okay, so it's the product of the potential difference over a component multiplied by the current through that component. Now, you don't always have these two. Sometimes you might have the resistance and the potential, or the resistance and the current. So I'm going to show you how to derive the other formulas for power. This is our main formula for power. I'll show you how to derive the others, but they are all on your formula sheet. Okay, so the way we do it is by using Ohm's law. Okay, so let's say we want to get a formula for power. So this is the formula for power when you know potential and current. Okay, let's say I wanted to get a formula for power if I didn't know the potential, instead I knew the resistance. So let's say I want a formula for power that has resistance and current in it. Okay, in order to do that, that means I need to get rid of potential difference, using the fact that I know potential difference is equal to IR. So instead of V, I'm going to write IR times I. And what is IR times I? That is just I squared times R. Okay? And then the third option is if I knew, what am I missing? Okay, so let's say I didn't know the current at all, instead I knew the resistance and the potential difference. Okay? That means if we were looking at this original formula, I'd want to get rid of current. So to get rid of current, I is equal to V over R, right? So I can write V over R instead of I. This is looking a little bit strange. Nope, that's right. Okay, so let's go for it. So we're going to have P equals V. Now instead of I, I'm writing times V over R, which when we simplify becomes P equals V squared over R. Okay, so these, where's my green? These, 1, 2, 3, these are your three main formulae for power, and you use the formula depending on what you know. So if they ask you to determine the power through a certain component and you know only the resistance and the current, you're going to use not that one, this one, right? You're going to use the formula that has resistance and current in it. Okay, so that's power. That's pretty much all there is to it, obviously, other than using the oh no, wait, that isn't. Okay, on your note, now let's carry on going with how it's set up on your notes. Okay, we're going to do energy next. Okay guys, so looking at energy, it is the product of the rate of energy transfer and the time over which the transfer took place. So it looks a little bit scary, but let's just unpack. Rate of energy transfer, that is just power. Okay, power is the rate of transfer of energy. And so we're taking power and we're doing the product of power, so basically power times the time over which the transfer took place. So this basically gives us our formula. Okay. Okay, before we can do the formula, we need a symbol. The symbol for energy is W or E. Okay, Usually it's E, I don't know why, but in electric circuits on your formula sheet it's a W. So I'm going to stick with W so you don't get confused when you get to your exams. On your formula sheet they use a W in circuits for energy, so we're going to stick with that. And our unit of measurement is joules. Okay. Joules, which is J. Okay, and this definition basically gives us our main formula. And our main formula is that energy is equal to the product of the power of a dissipated by a component multiplied by the time over which that energy, that power was dissipated. Okay, so it's a product of the power times the change in time. Now we've got 3 formulae for power, so we've got 3 formula for energy as well. So we've got W equals P times delta T, which can be rewritten as W equals the first power formula is that power is equal to V times I, right? So that means W is equal to V times I times delta T. Okay, the second power formula is that power is equal to V squared, I'm doing this in the wrong order, sorry. I squared times R, which means when we translate this to the energy formula, we're going to have energy equals power, which is I squared times R times delta T. And then our third equation for power was that power equals V squared over R. So when we put that into terms of energy, which is a W in circuits, is equal to power, which is V squared over R, times delta T. Okay, so those are your formulae for energy. So you've got the 3 main ones, the 3 that you're most likely to be using, and then you also have this one on your formula sheet. Okay, and there is actually a copy of the formula sheet on your note. Okay, then the last thing that I want to talk about before we do an example is the kilowatt hour. Okay, so I don't know if any of you guys have prepaid electricity, and when you or your parents buy electricity, they might talk about how many units you have. Those units of electricity are kilowatt hours. Okay, you are charged for electricity in your household per kilowatt hour. So that's what we're going to have a quick look at now, the kilowatt hour. Okay, or kWh. So, if you can determine the power rating of a component, if you can determine how much power is dissipated by a circuit or by a specific component, and you know how long you're going to be using that component for, then you can determine the kilowatt hour. Okay, so just quick, very important, when we were looking at energy, okay, with the W equals P times delta T, this delta T, the units are seconds. Okay, very important there. Delta T in physics is always in seconds. Got it. But as you can see by what this is called, the kilowatt hour, this is the one and only time we're going to use hours in science. Okay, the only time we use anything other than seconds for time is here when you're dealing with a kilowatt hour. Every other time it's seconds. As soon as it's kilowatt hours you're dealing with, you use hours. So if you know the wattage, if you know how much power something dissipates, and you want to convert that into kilowatt hours, the conversion is as follows. Okay, to get to kilowatt hours, you take your power that you've worked out in watts, okay, and you're going to divide that by 1,000, because there are 1,000 watts in a kilowatt. And then you are going to multiply that by how long you are using something for. So let's say I talk about boiling my kettle. Obviously, the more often and for the longer that I boil the kettle, the more electricity it's going to use, right? The more my electricity bill will be at the end of the month, depending on how long I use that kettle for, or how long your geyser is running, or how long you leave the fridge door open. Okay, it's going to use electricity for a longer time, so it's going to use up more power, more kilowatt hours, more money. Okay, So you take the power, convert it into kilowatts, and then to make it kilowatt hours, you then multiply it by the number of hours that that thing is in use for. Okay, so you multiply it by the number of hours that it's being used for. So if I use my kettle for a total of 20 minutes every day, let's say I boil the kettle like 6 times in the day, so I use the kettle for a total of 20 minutes every day, then that, how many hours is that? 20 minutes is the same thing to convert minutes to hours, you divide by 60, hey? So 20 minutes equals 20 over 60 hours, which is 1/3 of an hour. So you would multiply by 1/3 there. Okay, so you take whatever time is given to you, convert it to hours, and then take your watts, convert to kilowatts, times by the number of hours that appliance or whatever it is being used for. Okay, so we're going to, actually let me pause you, we're going to do an example. This is not so tricky, this section. Oh, I'm just noticing you didn't see that at the top. This is not that tricky. Tomorrow is going to be tricky. For this stuff, I hope you're coping. Don't get bogged down with all the different formula. None of them are tricky. It's just a case of choosing the right one depending on what information you have. Okay guys, here's our example. So we've got a little circuit here on the left. Very, very, very simple circuits. Okay. Usually with your electric circuits questions, it'll be one question in your final exam. Obviously in your upcoming exams, if we ever do them, it's going to be heavily focused on electric circuits because it'll be a term 3 exam. I'm not even sure. I don't know. Okay, usually at this stage in the year, we would be doing a test just on the last like 2 topics. So it would be no, it wouldn't even. It would be electrostatics and circuits. Okay, so there it would be quite heavy. But in your final exams, final grade and your final matric exam, it'll be one question. And in that one question, it'll be like a normal circuits question, like the grade 10 circuits question with a bit of internal resistance, which we'll learn tomorrow. And then the last like 1 or 2 questions will be something to do with energy and power. Okay, so it's not normally so heavily weighted where it's so much about energy and power. Anyway, okay, so straightforward circuit. We know that is resistor 1 with a resistance of 1 ohm. We know this is resistor 2 with an unknown resistance. Our cell has a terminal potential of 6 volts, and they also tell us that the current leaving the cell is 0.25 amps. Okay, and the first question is to determine the resistance on R2. So we know the drill by now. Either I can use Ohm's law if I know enough information, which I don't, right? I know the current because the current, this is in series, so the current here is the current there, but I don't know the potential difference here. So I can't use Ohm's law. Let's use the other option, which is our understanding of resistors in series. I know that the sum of my resistors must give me the total resistance, but I don't know the total resistance. So now I'm in a bit of a bind. If neither of your 2 options works, it means you need to make a 2-step answer. Okay, it means you first have to find something else in order to find what you want. So we want the resistance of this. Now there's loads of different ways of doing this. I'm now going to do it a different way to how it's done on your page. How is it done on your page? On your page, we first determined the total resistance using Ohm's law and then said 1 ohm plus that must give me the total resistance. Okay, so what I'm going to do is I'm going to work out what the potential difference is here. Okay, using Ohm's law, because I can do Ohm's law there, right? I know the resistance here, and I know the current there. So if I can work out the potential difference here, I know that the potential there plus there must give me 6. Okay, so that's the way I'm going to do it on the board. Different way to how it's done on your notes, just to show you there are lots of different ways of doing these. Okay, so I'm going to say for resistor 1, the potential of resistor 1 is equal to the current through resistor 1 multiplied by its resistance. So this is 0.25 multiplied by 1, which is 0.25 volts. Okay, I haven't budgeted enough space, so I'm moving over this side. Okay, that means that because my total potential difference must equal the potential of resistor 1 plus the potential of resistor 2. That means 6 volts must equal 0.25 plus V2. What am I doing? Why am I going with such a long route? Oh, well, it's fine. We'll carry on doing it with this route. Okay, so that means that V2 is equal to 0.75 volts, and we want the resistance there. I'm moving up here. Okay, so now we can do Ohm's law over resistor 2. So V2 equals I2 times R2. V2 is 5,75, sorry, 6 minus 0.25 is 5,75. So we've got 5,75 equals current through resistor 2 is 0.25 times the resistance, and we get that R2 is equal to 23 ohms. Okay, so we have R2, that is 23. Okay, question B. Determine the power dissipated by R2. Okay, so we actually now know enough information, after the way I've done it here, we know enough information to pick any of the three formula, right? We know the current here is 0.25. We know the potential difference is 5,75, and we know the resistance is 23 ohms. So we can pick any of the power formulae. Remember the power formulae? We're either going to go V times I, or we're going to go I squared times R, or we're going to go V squared over R. Sorry, let's try and remember it there. Okay, those are our three options, and we have enough information to pick whichever one we want now. In your worksheet, however, we only knew the resistance and the current at this stage. We hadn't worked out the potential. Okay, so just to keep it fun, I'm again going to use a different method. So let's use the fact that we know the potential. Let's use the ugliest of the three formulae. Okay, that's that guy. Some people would say ugliest, I think the most interesting looking. Okay, so the power dissipated by R2 is V squared over R. I can use this because I know all the information. Okay, I'm going to substitute in. So the potential over the second resistor is 5,75. I'm going to square it over the resistance. There is 23. And you stick that in on your calculator and you'll get 1,44. Okay, and remember our units are watts or joules per second technically, but we stick with watts. Okay, question C. Determine the energy used by R1, that's this guy, in an hour and a half. Sorry, that's what that says. Okay, so determine the energy used by R1 in an hour and a half. So energy, this is the W there. So we've got a pick of our energy formulae. I'm just going to write them here because there's more space. We can either use P times delta T, or we can use VI times delta T, or we can use I squared R times delta T, or V squared over R times delta T. Okay, let's look which one is helpful. So R1, we know the resistance. We know the potential and we know the current. Okay, so again, we can pick any one we want. So again, I'm going to pick, okay, we use the V squared over R here. So let's use I squared R, just for fun. Okay, because we can. We have enough information. So I'm going to use that W equals I squared R times delta T. So that's the current through resistor 1 is the same current everywhere because it's a series circuit. So it's 0.25 squared times the resistance of resistor 1 is 1, and then delta T. Delta T in physics is always in seconds, always. Okay, the only time we use hours in physics is when you're converting something to kilowatt hours, which we're not doing here. Okay, so delta T must be in seconds. I have an hour and a half, right? So that's 1.5 hours. I need to change that to seconds. So if I times that by 60, I'll have it in minutes. And if I then times it by 60 again, I'll have it in seconds. So you're going to have to times it by 60 twice to get it from hours to seconds. And as our final answer, we get 500. okay, on your note, it says 2,5. Okay, I'm going to change it and then upload it again. Some of you, your notes might say in the answer there 2,5. It should be 1,5. Okay, which means the answer is wrong, so I must type it in. So it's 0.25 squared times 1 times 1.5 times 60 times 60. And we get 337,5. Okay, and energy, which is W, is measured in joules. Okay, please don't get mixed up there. I'm actually gonna just quickly use this space before we do the last question. Okay, power versus energy. Okay, so power, the symbol is P, the units are watts. Energy, the symbol is W, the units are joules. Okay, don't get these mixed up. I know it's going to be easy to mix them up because the units for power is W and the symbol for energy is W. So just keep a good look on that. Keep an eye on that you're not using the wrong W. Okay. If it says energy, the symbol is W, the units are J. If it's power, the symbol is P and the units is W. Okay. Okay, last question, question D. If electricity costs R1.75 per kilowatt hour, how much would it cost to run the circuit for 45 minutes? Okay, now I know that there are some of you saying, but ma'am, a circuit is free to run because it's a battery. I know that. We're imagining a scenario where instead of a cell, we've just gone and plugged this thing into a wall. Okay. So it costs R1.75 per kilowatt hour. Alarm bells should be going off. We need to do something there. We need to do a conversion. How much would it cost to run the circuit for 45 minutes? The whole circuit. Okay. So remember, kilowatt hours, this is power, right? We've got to know the power to convert the power into kilowatt hours. But it's not the power of resistor 1 or of resistor 2, it's the whole circuit. So that means I need to actually do three things here. I first need to find the power, then I need to take that power and convert it into kilowatt hours, and then we can say, well, I know the cost per kilowatt hour, so I can therefore work out the cost in total. Okay, those are the three things we have to do here. So starting with power. The power of my whole circuit, what do I know? I know the total potential and I know the total current. So we can use the easy one. P equals V times I. So P equals 6 times 0.25, so it's a quarter of 6, which is 1.5. Let me just double check. 1.5. Okay, 1.5 watts. Okay, so that's step 1 done. Step 2, convert that to kilowatt hours. So we're going to take 1.5 watts, we're going to divide it by 1,000 to get it from watts to kilowatts, and times it by the number of hours we are using this thing for. So we're using it for 45 minutes. Okay, remember this is the only time we use hours instead of seconds. So we're using it for 45 minutes, which is 3/4 of an hour, right? So 3/4 or 0.75. And when we convert that, we get 1,125 times 10 to the minus 3. Okay, so very, very low electricity usage actually. Okay, and we're not done. We now have to work out how much this is going to cost. So this really takes us back to grade 8 and 9 maths. If it costs this much per thing and I have this many things, then how much will it cost? You multiply, right? It costs 1.75 per kilowatt hour. I have this many kilowatt hours, so I must multiply. Okay, so the total cost is going to equal R1.75 multiplied by 1,125 times 10 to the minus 3. And we get something very small, if I remember correctly. We get 1,97 times 10 to the minus 3 rands. Okay, which is very small. It's 0.00197 rand, which is basically the same thing as 0.2 cents. Okay, not even a full cent to run this circuit for 45 minutes. But like I said, this is an incredibly low wattage circuit. More likely, I mean, if you were running a kettle for 45 minutes, I mean, it would cost you upwards of 100 Rand. Okay, yeah, that's it. That's all the examples. The questions are also quite straightforward. This is like a nice little easy thing of the grade 11 circuits. Tomorrow is internal resistance, which can get quite tricky. It's not that bad if you just stick to the formula, but actually wrapping your head around what's going on, it can get quite tricky. No, you can't see the bottom of the board. Sorry, it was just that. Okay, cheers guys.